what we are going to do today is to start looking a little bit more detail at the problem of scheduling, and essentially the problems that we are going to be dealing with is how do we construct systematically architectures as well as schedules that basically allow us to map somewhat complicated functions onto hardware. Now, one thing to keep in mind during this entire discussion is the examples that we are going to be taking up in class are relatively simple examples. What I mean by that is they are going to be examples that we can actually draw out and understand within the 45 minutes of a class. But what is more important over here is the underlying principles. What are the ideas that we are making use of in order to get the implementations that we are targeting, right? So what are the basic concepts? What do we mean when we talk about an allocation of resources, the binding of functions to resources, the scheduling of the operations on the different functions, right? And what impact do they have on the final hardware and the optimality of the implementation that you get? That's essentially what we are going to try and understand by means of the examples that we will take up. But what you need to keep in mind is, at the end of the day, you are not expected to directly implement these things. You need to understand them in order to understand how the high level synthesis compilers work, because the compilers essentially are going to take up the task of taking the operations that you have written out in the form of C code and converting them into an equivalent hardware implementation, which means that when you finally see the result coming out of the high level synthesis tool, in order to understand all the different factors as well as why it gave a particular solution, it helps if you understand how the approach that is typically followed, at least broadly. Okay. So before getting into the details of some specific scheduling algorithms, what we are going to do is take up a simple example to also illustrate a few basic ideas as well as bring out some of the terminology that we will need in order to understand things going forward. Okay. So I am going to take one very simple graph to be scheduled. Okay. It's a data flow graph that looks like this. So the numbers in red over here are the execution times of these functions, right? A, B and C are three operations in a data flow graph. I have some kind of hardware that is capable of executing these functions. I am not telling you how many such hardware. That's essentially a question to be answered as we move forward, right? How much hardware do we need, etc. All that I am saying is, on whatever type of hardware, it might even be a general purpose processor where A is a function, B is also a specific function, etc. A takes 40 units of time to execute, B takes 20 and C takes 10. Okay? And obviously there has to be some delay elements somewhere on the graph, because I do have feedback loops. Right now I am going to assume that this is the distribution of delays that I have. Okay? And the question that we are going to ask is, first of all, what is the best possible iteration period that I can get? And if I want to achieve that iteration period, how do I go about doing it with a minimal amount of hardware? Okay? So to answer that first question, what is the best possible iteration period that you can get for a graph like this? What does that mean? What am I asking for? The iteration period bound. And how much is it in this case? 35, right? So basically what I have is, there are two loops over here. This is one loop and this is the other loop. Okay. So if I compute the two loops, it essentially turns out to be max of 20 plus 10 divided by 1, that is the B to C loop, and there is also the 40 plus 20 plus 10 divided by 2, which is the ABC loop, and this max turns out to be 35. Okay. One interesting observation, you can see that the iteration period bound is actually smaller than the execution time of A. So even though A itself takes 40 time units, what we are saying is, on average I should be able to complete iterations in time even less than 40. Now how does that happen? Obviously that means I need to be running things in parallel. Okay. So now let us look at how do I actually achieve this, how do I get to this point where I can get an iteration period, an average iteration period of 35 time units. Okay. So I am just going to take up the sort of trivial method by which I would go about doing this and say, all right, let me start and just write things out, right. I mean, I can see the graph as it stands right now. If I was asked to manually start executing it, what could I do? The first thing I can see is the different instances of A and B and C. What are the ones that can execute right now? What are the actors in this graph that are ready to fire? Only A, right, because C has an input from B that does not have any delay tokens on it, it does not have any ready initial conditions. B has an input coming from A, same story, there is nothing available on its input. B also has another input coming from C which has a token on it, but that does not help, I need tokens on both its inputs. And A on the other hand has 2 tokens ready, 2 initial conditions. It is like, you know, the C of -1 and C of -2, both data are available, I can use them in order to compute the A of 0 and A of 1. Okay. So, what I am going to do is write that down. I will say that A0 can start executing at time 0, and how long does it take? It takes 40 time units, therefore, it completes at time 40. Okay. What happens after A executes, after A0 executes? Now B has enough inputs, which means that I could execute B0 if I wanted to. It would start at time 40, it has to wait until A finishes, A0 finishes, and it would run till time 60 because it has an execution time of 10 time units. Okay. And once B0 has executed, it means that it puts a token on the B to C edge. Data is now available for C, which can now execute, and C0 will complete by time 70. Okay. Now, if I had only one processor available to me that was capable of executing A, B, C, everything, right. Fundamentally, the only thing I can do is, after this I can start once again with A, right. I can start A1, which would go on till time 110. I could do B1, which would go on till time 130, and then C1 would finish at time 140. Okay. Now, all of this could execute on a single processor, and if I had only a single processor available to me, this is pretty much the only thing that I can do, right. From a hardware utilization point of view, what can I say about it? What can I say about this schedule that I have given? It is a perfect schedule, right. Hardware utilization is 100% because I have only a single processor. At any given point in time, it is executing either A or B or C. There is no problem with it. Okay. So, in terms of the efficiency of the schedule, this is fine, this is doing exactly what I require it to do. Okay. But now, what if I had 2 processors available? Now, what I could say is, the first part of it remains essentially the same. A0 executes here from 0 to 40, B0 executes up to 60, and C0 executes up to 70, but there was nothing preventing me from running A1 as well. A1 will also run from 0 to 40. As soon as A1 has completed, now B1 also has the data that it needs. Actually no, B1 does not have the data that it needs. Why? Because until C0 completes, B1 cannot execute. Okay. So, what happens now? It essentially means that B1 can start only here. Okay. So, I start at 70, finish at 90, and now C1 can execute and will finish by time 100. Now, where does this leave us? Have we, what does this actually mean? Now, what this is telling us effectively is that the time required, I was able to finish 2 iterations within 100 time units. So, the iteration period, not the iteration period bound, the actual computed iteration period in this case, average is 100 by 2 equal to 50 time units. Okay. This diagram that I have drawn over here, by the way, has a specific term that is used for it, which has actually got nothing to do with hardware scheduling or designing VLSI systems or anything of that sort. It comes from the domain of operations research. It is called a Gantt chart. The idea of a Gantt chart is, like I said, it actually comes from the domain of operations research. It is essentially saying if you are planning a project, right, you have a set of tasks that need to be completed in order to complete that project. There are the initial conditions, right, deciding what are your main goals, what are the things you need to do in order to achieve those goals. You might need to buy some hardware, you might need to assemble some things together, you might need to do some writing code, you might need to read up on background literature of things that have already been done. There are certain things that can straight away be done. So, reading up on the background and deciding what hardware to buy can be done straight away, you do not have any other dependencies. But you can't start putting things together until you have bought the hardware, until you have completed that step, right. So, Gantt charts are used in general for any kind of project planning in order to capture the set of dependencies that you have and how they sort of cascade one into the other. Okay, and they finally sort of tell you how long does it take to complete a certain set of operations. Okay. So, typically they would be accompanied by certain kinds of milestones or quarter wise breakup. All those are from the domain of project planning. Exactly the same set of steps occur even when you are trying to take a system that you have, a data flow graph, and map it into corresponding hardware. Okay. So, now the question is, what happened? I got to an iteration period of 50, but is it possible for me to get down to 35, which after all is my target? What could I have done over here?